Alright, our first lesson of this chapter has to do with freefall and gravitational acceleration. So the definition of gravitational acceleration is simply the acceleration that all objects have due to gravity. So all objects fall with the same exact acceleration, no matter what size they are. Gravity is going to be the same for every single object on Earth. Earth itself has a gravity of 9.81 meters per second squared. So it falls with that gravity. Every single object is falling with that same gravity, no matter what size it is. You may question this a little bit because of the fact that the bigger something is, it seems like it's going to tend to fall more quickly than other objects. But because of it being bigger, the force is going to have to balance that out more because it needs a bigger force to get that going. So it takes more force to get that object to move, but the weight behind it is the force that's causing it to fall. So it all balances out to being the same exact acceleration, even though on Earth things don't always hit at the exact same time. They're accelerating at the same rate, but they're not hitting at the exact same time. Now, the reason that happens is due to something called air resistance. So air resistance is air resistance occurs when the Earth's atmosphere, the air molecules that are surrounding, obviously we know there's air all around us, those molecules have mass, and that mass causes friction. It causes a fluid friction that happens between those molecules and everything that's moving through it. So if you move your arm through the air, we did this when we talked about fluid friction. I said move your arm around. You can feel that there's a resistance there. That is air resistance. Air resistance causes things to slow down as they're moving through. That's why when they design things like planes and things that are meant to go through the air, they make them more aerodynamic to try to reduce the air resistance as much as possible. So that's what causes different objects to hit the ground at different times, even though they're accelerating at the same rate. That is the only reason that happens, and we're going to watch a video where they drop objects in a vacuum, and a vacuum is a place where there's absolutely no air whatsoever, and to show you what the effect is with dropping them in a vacuum as opposed to outside of a vacuum. But either way, the acceleration is still going to be 9.81 meters per second squared. That is gravity on Earth. So here just kind of illustrates what the effect the air resistance has. So gravity is a large force pulling an object down. The square there is meant to represent our object. Air resistance is a small force that is pushing it back up. It's resisting that downward pull. So the net force, which we know is the total ending force, is going to be less than what gravity is, less than what its weight is, simply because air resistance is taking some of that force away. So the size and the shape of the object is really going to determine how much air resistance acts on it. If we have something that is more compact, it's sleeker, there's going to be less air resistance as compared to something that is flat and has a lot of surface area. Drop a piece of paper, you're going to see it floats gently towards the floor. Drop a crumpled piece of paper, then you're going to see that's going to fall a lot faster than that flat piece of paper. So there's definitely going to be a difference there, considering their surface areas are different. There's more air resistance with the flat piece of paper, so it goes slower. And the last thing with this lecture is terminal velocity. So terminal velocity, the definition of that is the amount of air resistance of an object on an object. It's going to increase as the speed of the object increases, but it's going to hit a point where it does not increase anymore, and that's called terminal velocity. So if let's say you drop something and it falls and it falls and it falls, if it never hit terminal velocity, it would just keep increasing until it hits something. But that doesn't happen. If you throw a baseball in the air, it's eventually going to hit its peak and it comes back down, and it'll speed up for a while, but eventually it'll just stay like it's on cruise control. It'll hit that terminal velocity. It'll hit its max speed, which is a good thing, because if, for those of you that play baseball, if that kept speeding up, it would hit your hand at a very, very high rate of speed. So it does, because of air resistance, hit a certain point where it meets it's equal to the force of gravity. So it's going to cause it to move at a constant speed and not accelerate anymore. And that's what terminal velocity is.